last physics video. Yes, I did this video already once, playing Richard Feynman video, but it is a little bit, there's a lot of unnecessary bits in there, so I just figured I'll try again. See if we can make it a little more concise. So I'm at the part where he's talking about the rules of physics, or gravity in this case specifically, and he calls them laws. I'll say the rules just because it's not going to be violated, it's that they're bendable, some of them.
Of the universe and so on, and there were considerable arguments about this.
Right, so this is the, you can't really see it, but F, and then the mass, and divided by the square of the distance is the, kind of famous, whatever, inverse square rule, which is basically just means, to do a simple drawing like a Hoflade here, we just put a square in and then realize the larger square created here would be 4 times. So as you double the distance, 2x the distance, you end up with 4 times the area shielded. And this, the important fact is this is a rule created by straight line interaction. So this is a a photon kind of rule, a rule of again, something with straight vectors. No pressure can go inside here. Nothing can bend in. So this is a rule created by straight line geometry. And that should just be kind of a giveaway, because this same rule applies not just to gravity, but also to magnetism and electricity. And that's sort of important. I think it's fundamentally a giveaway, but the fact that it's all photons that do this straight line thing, it's also sort of a giveaway that maybe the photons are made of something. That something is gravity and electricity and magnetism as forces, and I would argue that's the truth, that it's all just these quanta, and all they're really exchanging is directional information. But we'll get to that in the next clip maybe. So we'll go through, so this is the first rule, is the inverse square. We'll just put 1 over r squared for the inverse square. And move on. Yeah, the next one's going to be ellipses, and then, which isn't a rule, that's a tendency. It isn't a law, it's a tendency. And then, that orbits end up in ellipses. And then we'll move on to the other bits, which are the equal distance area swept in an orbit, and that has to do with the velocity as you move closer and away from the center of mass, the center of gravity. And the other one would be the speed and distance rule. Don't know what can't remember what it's called. We'll get to it. Be back. Alright, I'm back. Let's see if we can explain this. So look, the fundamental principle is really quite simple. So if you just think of all of the universe is just made out of little quanta, and they move the speed of light in a direction, and they can never change size, and they can never change their speed. And so all that really happens in all interactions in the universe is these quanta are basically just exchanging directional information. So one comes in going, or a group, or the net amount of something. So when something's moving, it has a net imbalance of these little arrows, in that it has collected arrows, and it has collected more going in one direction than going in some other direction. That would be a simplification, but it works. And that when it's interacting with something else, it's attempting to exchange these arrows. It's giving away some that are going this way for some going in some other direction. And that's essentially what's all matter's made out of. And the key thing to understand is that that's how these quanta interact. Now there's a little bit subtle difference that when you have a photon, it's a pair of these quanta tied in a frequency relationship, so they have a set distance between them. And when they interact with an atom or an electron, they're of the correct frequency where they're actually absorbed into an orbit. So they're actually coming in at the right pitch, attitude, where, as will be explained with inertia and these different other principles of gravity and big celestial orbits, there's just a particular, you have to be at a particular attitude in approaching a gravitational body to be captured by that gravity. So, you know, either you can't be going too fast or you go through the gravity. And if you're going too slow, you get absorbed by the gravity. You get pushed into the mass in the center. So, but regardless, so it becomes important in understanding the idea of what velocity is in any body is really a movement of stored energy, stored quanta, ones that have been absorbed. So the difference between light and gravity is that light is absorbed often by matter or bodies that have electrons, and the regular non-frequencied photons, or you call them gravitons, aren't absorbed. They just interact with the pieces of an electron and exchange directional information. So they tend to make the electron want to go a different way because it now has a vector, another vector going in that direction. It's collected an arrow that has that directional information. So if you just think of things collecting arrows, it might make this more, at least intuitively, understandable. So we'll move on to the next little segment here. He'll get on to the idea that all orbiting bodies that we know of, planets, you know, the big stuff, end up in ellipses.
This was too big for Tycho Brahe to have made an error, and that this was not the right answer.
Oh, okay.
So because of the precision of experiments, he was able to proceed and find that, to go on to another trial, and found, in fact, ultimately this. Three things. First, that the planets went in ellipses around the sun, with the sun of the focus. An ellipse is a curve all artists know about because it's a foreshortened circle. What children know about because somebody told them that if you take a string and tie it to two tacks and put a pencil in there, it'll make an ellipse. These two tacks are the foci, and if the sun is here, the shape of the orbit of a planet around the sun is one of these curves.
Okay, so now the Earth isn't quite that eccentric, but you know, it's an ellipse. But the point being is that there's a point where it's closest to the sun and further away from the sun. Like I said, this is sort of the Earth isn't quite that extreme. And you know what's happening though, theoretically. So this is what you'd call this off-center kind of orbit. But the real catch to it is that mechanically, it's going to function as if this was a perfect circle. So no matter what you do to the circle, the dynamics will always balance to being the same as if it was a perfect circle orbit. So it'll change speed or change something else to accommodate the fact that something has changed in some distance relationship. So there's a certain geometry. Well, that's the next argument. So first let's just deal with this ellipse argument. In the sense that, okay, so if a body was coming into a gravity, so this is the gravity, and it was coming in at certain angles, well, depending on the angle it's coming in, the speed is going to dictate this shape. Now, it's a rule, like he says it's a law, that these are always ellipses. But it's not really a law. It's just that probabilistically, it's almost impossible to come in at the correct pitch and speed to create a perfect circular orbit. So it's really just the fact that you're allowed a range of error. So it's like you could increase the velocity of the Earth a little bit and it would still orbit the sun. You could decrease its velocity a little bit and it would still orbit the sun. It would just have a closer orbit. It would end up in a closer orbit. So you can always change elements. There's a range where you're still going to be captured by the gravity and not consumed by the gravity. and that range is wide, but everything in that range is just a variation on the ideal circle. So, you know, what the exact probability is, 1 in a million, I don't know, but it's not like it's a law that it can't be a perfect circle. It's just that the law of probability is it'll be an ellipse. So I just want to clarify that. I think that's the only part that's important here. So I will move on to the next bit. Be back soon.
On this, that if you put the position of the planet down at two times separated by some definite time, let's say 3 weeks, and then at another place in the orbit, put the positions of the planets again separated by 3 weeks, and draw lines from the sun to the planet, technically called radius vectors. Anyway, lines from the planet.
Okay, so the point is the same amount of area will be swept in the same amount of time. So if it's, you know, 3 weeks in this example, you would add up the area. So something would have to go faster here to be able to create enough area to be equal to this area. So it has to go slower out here, and it has to go faster here towards the focus. Now this is a symptom, in my opinion, of the real dynamic. And the real dynamic is that the closer you are to the gravity, the more you're falling. So the more you're being pushed in another velocity direction. And so you end up with two velocity vectors. You end up with this body wants to go in a straight line this way. You know, well, here I guess it would be this way. And it's going to be pulled down this much by gravity. And so you have to add those two vectors, essentially, and it's the one in between them that it actually traveled in a sense. From its perspective, it traveled this distance, this arc distance is its actual travel, and that is more than its actual velocity in this direction and the addition of the velocity in this direction. It can't do two velocities. It always has to turn the velocity into a single direction. It can't go, you know, if something's already moving this way and I push it this way, it can't do both directions at the same time. I mean, over a period of time. It's always going to be the average of those two directions that it's going to end up moving. So it's actually going the same speed, it's just traveling more distance, which ends up looking like faster from our perspective. But again, what's really happening is over here it's actually going faster than it looks, because what you really have to do is just pretend it's a perfect circle, because technically it's a perfect circle if you really add it up. If you just subtract what you added over here, it ends up being the same difference. So it has a net speed to make the orbit, and the net speed is more of a reflection of what's actually happening. Yeah. But anyway, the point is here is that it's the added velocity that creates the added velocity. It's obviously got more velocity. This has less velocity in this direction, and this has more velocity in this direction. So there's more gravity, more feet per second it's falling than it's falling over here. And it's just that difference that creates this extra velocity in the combined, when you combine the two vectors of movement. So it has the same velocity going its way, but depending on the gravity is adding more velocity in another direction, and you have to average the two vectors of direction to find out the real, what it ends up going. You know, so that's enough of that. But this geometry of it is just a symptom of the fact that it's always a circle. And these will always end up being the same because the gravity is always stronger closer. So it's really the relationship for the fact that you're accelerating towards the center of gravity faster as you're closer, and that's really all this is happening. So it's not that significant. I guess the significant thing to understand is this directional exchange that's taking place, and that's what's creating this extra vector of acceleration. So as this center of gravity creates this blockage of the gravitons coming from this side, there's more coming from this side, so there's a net imbalance. So for every exchange that takes place, there's more exchanges that are just saying it's collecting more arrows going this way. So this body, as it's in this gravitational field, just ends up collecting more arrows going down in this direction than it can collect going in this direction. And that imbalance is what's just changing the net velocity, because it's collected those arrows, it still has the arrows going this way, and it ends up in net moving on this arc. I think that's good enough. Till next time.
Several years later, he found the third rule, and that had not to do with the exactly motion of a single planet around the sun, but related the various planets to each other. And it said that the times that it took the planet to go all the way around was related to the size of the orbit, and that the times went as the square root of the cube of the size of the orbit, and for the size of the orbit is the diameter all the way across the biggest distance on the ellipse.
Yeah, so I don't know if that one's too relevant to anything that I need to add anything to. It's just basically making this argument that a circle is a circle. Whether you stretch it or compress it or widen it or whatever you do to it, it's still fundamentally a circle, and that's the rule of circles, is that if you're going a certain velocity, it has a certain, you need a certain pressure to be able to create an orbit. And so there's just a relationship that has to do with cubing and squaring that will define that range of velocity to the size of the orbit in net. But it doesn't really matter if you go faster at one end or slower at the other end. It's just the net velocity, the overall period it takes for you to make an orbit, is what's always going to be tied to the size of the orbit.
So,
I mean, it really doesn't matter the mass. The thing that matters is the velocity. So a baseball could be in any orbit as long as it has the appropriate velocity for that orbit. And a giant planet could be in the same orbit as a baseball, and it just doesn't matter. They both have to have the same velocity. So it doesn't matter what your mass is, it just matters what your velocity is, where your orbit will be. And it's certainly, if you have a perfectly circular orbit, each velocity would have a perfect circle orbit. It would just be right after each other. 10,000 miles a minute, 10,001, 10,002, they'd all have exact perfect circle orbits that you'd go into regardless of your mass, just based on your velocity.
Has these three laws, which are summarized by saying it's an ellipse, and that equal areas are swept in equal times, and that the time to go around varies as a 3/2 power of the size, the square root of the cube of the size. So there's three laws. Kepler.
Right, so whoops. Well, that's a bad thing to have happen. Back to the beginning. We'll try again. I just play this bit just to illustrate that he's making a joke here, but it's it's kind of a backfire kind of joke.
Time of Kepler, the problem of what drove the planets around the sun, was answered by some people by saying that there were angels behind here beating their wings and pushing the planet along around orbit. As we'll see, that answer is not very far from the truth. The only difference is that the angels sit in a different direction and the wings go in.
Yeah. Again, Feynman was kind of a part of this mob that debunked, argued against a particle theory of gravity, and he did so, without much rigor to his argument, and based on his authority, that was all that was needed. Feynman says so, and everybody just followed along. So, because the truth is, yes, it's not angels, but it is pressure, and it's a pressure being applied by space itself that's full of this energy, more energy than in all the matter in the universe. Certainly, much more. This free energy that is not captured, that only exchanges this directional information. So let me just do this real quick just to make sure you understand that what the quanta is just a thing, and a thing with direction. So it has a fixed mass, a fixed speed. It can't change its mass, it can't change its speed, and it has a direction. It's at the speed of light that it goes in. And when it interacts with another one going some other direction, the interaction is just purely kinetic. Two things come in going directions, and two things leave going exactly the same direction. And the key thing is that this one, let's say it was part of an atom, you can see that this is what's creating an orbit, so to speak. If it keeps getting knocked down in this way, in this manner, it gets caught in a perpetual trap. It'll just keep following that pattern. And of course, if it has some other body for which this gravity is being created, this pressure of keep getting hit it. So this is the pressure that's constantly around each body, has stuff coming into it all the time. And the only stuff that's relevant, right, there's a whole chaos of arrows going in all directions, but the only ones that are relevant, obviously, are the ones that are going to hit you or interact with you. And they're coming from all directions at all times, and gravity, or force, is applied when you are shadowed from that force. These arrows here wouldn't be shadowed by this body, and therefore this body would end up getting hit by more arrows with this directional tendency. And so you can kind of see if that what is exchanged here, this one leaves this way, this one leaves this way. They've exchanged directional information. This one is now doing what this one was doing. So it's just an exchange of direction. This one exchanged this direction with this one, which now is going that direction. So the two bodies exchanged direction. And so that's basically what matter's doing, is it's collecting directional information. And it's the orientation of these orbits that decide the balance of its directional information. So you can imagine if I was to take this drawing and simplify it into an ellipse, that what it might end up looking like is more than one arrow going in a direction, and the rest would remain the same. So it would have a directional imbalance. So there would be more arrow going this way than arrow going that way, and that would end up being something that would travel as it orbited, and that would be what we see as material velocity, or inertia. Inertia is merely an arrangement, a fixed arrangement. This could have a mass at the center, or it may not be necessary, but it's sort of irrelevant. The only thing that's relevant is to understand that it has extra this direction, and that's why it ends up moving in that direction. Any imbalance of arrows, a collection, more of. But the math of it is this simple. It's merely a collection of directional information, and that's what all velocity is based on. So he's going to get on the subject of inertia here, and that's where we'll pick it up. Velocity, perpetual velocity, innate velocity. I don't know what inertia would. The two words are kind of interchangeable. Inertia inertia you can have inertia without any velocity. Like, I appear not to be moving right now. I probably am, but I'm just saying I could appear to not be moving. So it is possible to have zero inertia as a material body. Quanta can never have zero inertia. They're always going the speed of light. They have a constant velocity, a constant inertia. We as a collection can have inertia in a net direction by collecting more arrows in a direction. Something like that. Alright, well, I'll find a clip appropriate to start again.
Discovered that idealization, a great principle called the principle of inertia, which is this: that if a thing has nothing acting on it, if an object has nothing acting on it and it's going along at a certain velocity in a straight line, it will go at the same velocity in exactly the same straight line forever. Unbelievable though that may sound to anybody who has tried to make a ball roll forever, the idealization is correct, and that if there were no influences acting, such as the friction on the floor and so on, the thing would go at a uniform speed forever.
Alright, so the point is that if it has arrows in a direction, something has more arrows, more quanta tending to go in a certain direction, the only way it's not going to go in that direction, the only way this is going to stop or change is something has to change it. Some new arrows have to be added, more arrows going this way, or arrows going the opposite direction to stop it. But arrows have to come in, it has to collect those arrows in exchanges of directional information, these purely kinetic things. It doesn't absorb the arrow, it just exchanges direction with the arrow. So it's not like it gains a new arrow, it just gains an exchange of directional information. So there's always, say, there's here 5 arrows. There's always 5 arrows. And all that changes is which direction the arrows are going in. So an arrow that was going this way ends up going that way, and now it has 2 going this way and 1. And you have to understand it has a period and it cycles, and there's forces that are holding this together. And that's a whole other subject. But the point is that the real factual, the net end is that all that's being really exchanged is directional information. Arrows are changed in their direction, and that change in direction is all that takes place. No arrow is absorbed, none is emitted. And so until some kind of arrow force comes in to change the fact that I'm being pushed by gravity in a certain way and I'm moving on the earth and all that kind of stuff, I have an absolute velocity relative to nothing, relative to a perfect circle. And when I'm not in a perfect circle, like right now, I'm probably not perfectly quiet as my matter. And net, it has a velocity in some absolute vector. I can't know that because I can't know all the conditions that I'm riding on. And you can never perceive your velocity in any direction outside of a force that's changing your direction. So when no force is applied, there's no sense of velocity. Regardless, yes, but the point would be is, let's say I had a net quanta. The net of my quanta is in that direction. The only way it can go some other direction is some gravitational force, some arrow source, some source of an imbalance in arrows has to give me more arrows coming from some other direction than it gives me from the opposite direction. I have to find an imbalance of gravity, so to speak, of energy, and that can change the orientation of my arrows by exchanging ones that are going that way for ones going some other way. In net. It's always a net equation over time.
The next point was made by Newton, who discussed the next question, which is, when it doesn't go in a straight line, then what? And he answered this way, that a force is needed to change the velocity in any manner. First, for instance, if you're pushing it in a direction that it moves, it will speed up. If you find that it changes direction, then the force must have been sideways. And that the force can be measured by the product of 2 effects. First, how much does the velocity change in a small interval of time? How fast is the velocity changing? How much is it accelerating in this direction, or how much is the velocity changing when it changes direction? That's called the acceleration. And when that's multiplied by a coefficient called the mass of an object, or its inertia coefficient, then that together is a force.
Right, so the argument is almost backwards, right? Because it's the fact of how much you have to move that will tell you how much force you need to move it. So it's not like it's a byproduct, this is the product. It's the mass that's just telling you, well, when you have a lot of mass, that means you have a lot of arrows to change. The more mass you have, the more arrows you have to change direction of. And it takes a certain amount of time to change all those arrows. So there'll always be a lag in the amount of time it will take before you can get that bigger thing up to having its arrows all changed to the new net balance. Yeah. The balance of the imbalance. The imbalance is always going to be accelerating your velocity if you stay in a net imbalanced field. So when you're in the pull of gravity, you will keep accelerating if you don't crash into something. If you don't hit the road, you'll just keep falling faster and faster and faster. If there's no air resistance or any other resistance, you'll just keep gaining velocity until you hit something. And so while a force is being applied, it keeps changing the arrows. And so what's effectively happening is the force is being applied, more and more of these arrows are getting changed in the direction. And eventually so many of the arrows will get changed, that you'll end up creating a velocity that's probably too fast to keep all of this together, and you end up just creating a stream of light. So if I took matter, this, and I accelerate it to the speed of light in a direction, it will be light. It won't be anything orbiting anymore. It'll just be arrows going in one direction. So as I make it go faster and I change these arrows directionally, I create more arrows going in this direction. You can sort of see that the more arrows I cross out this arrow and make this one, and cross out this one and make another one, and go in, the more I do that, the weirder and weirder and harder it's going to be to maintain any structure inside the matter, because all the quanta is being converted into quanta moving in one direction. So if you could have such a thing as a force that could be kept being applied, like a rocket ship with an engine that could apply a tremendous amount of thrust, and it could just keep applying that thrust, theoretically, in space, you would reach the speed of light, the speed of your thrust, in the opposite direction. Theoretically, eventually, all of your matter would be converted into equal and opposite thrust. Yeah. So I'll wait till I get to a good part. We might be here. Let's see.
One can measure for instance, if one has a stone on the end of a string and swings it in a circle over his head, then one can measure, everyone finds one has to pull. The reason is that the speed of
yeah, this wasn't too great. Yeah, just the idea that the heavier it is, the harder you gotta whip it to get it going, to maintain its speed. More force will have to be applied the heavier it is. Okay, till next time. Alright, let's pick up about here.
But further down, toward the sun. In other words, its velocity, its motion, has been deflected toward the sun. So what the angels have to do is to beat their wings in toward the sun all the time. That the motion to keep it going...
There you go. So that's basically the idea of particle gravity, is that the mass of the sun, its density, its atoms, it's not even its mass, just the individual atoms, are blocking arrows coming from one direction. The arrows from the other direction are still hitting, so there's more arrows coming in one direction than the other direction, and those arrows are effectively changing the arrows inside the body. The arrows aren't pushing it. The arrows are changing the arrows of the thing. So I'm exchanging arrows with gravity, so to speak. I'm exchanging directional information with gravity. Gravity is leaving in some other direction out of my body than the direction it was going, which is down. So the gravity comes into me, it leaves in some other direction. The tiny percentage that actually hits me leaves in some other direction. We can't really measure it because it's only 1/1,000,000th of the actual strength of the gravity. There's so much gravity. But anyway, density-wise. And only a tiny amount of it needs to change my overall net motion for me to move. I don't need a huge amount of net quanta moving in a downward direction to acquire velocity. It just takes a very small number of a small imbalance in the total number of my quanta to be in a direction for me to move in that direction. A small number creates velocities that seem to us very fast. But again, remember, the speed of light is 168,000 miles a second. We're talking millions of times difference between this inch of movement, this speed, and the speed of light. There's 1,000,000 times difference. And so it's only a tiny amount of extra quanta, extra arrows going in a direction to create this kind of movement. So, but as the gravity comes through, I'm just exchanging the directional information. The gravity comes in and it leaves. And all I did was keep the arrows going down. Gravity took the arrows going some other direction. That's the exchange. Yeah. I'll be back. Alright, this part is
Keep it
good.
going in a straight line has no known reason. The reason why things coast forever has never been found out.
Alright, so this is, and again, this is something that's part of, if you thought about this whole particulate theory and this whole exchange of directional information, this is the reason. Net imbalances, elliptical imbalances inside of the orbitals, inside of the matter. So it's not just the atom. The atom is an orbital system, but each one of the particles inside the atom, the electron, the neutron, the proton, these are all things built out of also things circling each other. So you have to think of these arrows aren't on the atomic level, they're on the subatomic particle level. The subatomic particles are made of these arrows. And it's their eccentric movement that creates movement in the entire atom, which creates movement in our bodies. So it's that granular. It's very granular. The real grain rate, the real foundational sand that everything's made out of, goes to these subatomic particles, and they're the ones that hold the quanta. They're the ones doing the exchanges of directional information. Not exchanges of energy, just exchanges of direction. Remember, exchanges of energies requires you to absorb the arrows, where you gain arrows. So when light comes into my body, hits my body, some of my atoms absorb the arrows that quanta is made out of, and they become part of the orbits, and then they can be released at some other time as another photon. But they're absorbed energy that becomes potential energy. They're not just kinetically reacting. They're absorbed and then readmitted as energy.
The law of inertia is no known origin. So,
right, so I think the origin is very simple. Well, whatever. What can I say? I think it is known now. So, yeah, I think it's known now. I know it. Let's see who else will know it. See what else it says.
oh, the angels don't exist, but the continuation of the motion does. But in order to obtain the falling operation, we do need a force.
Right. And the force is real, not space, not nothing. The force is quanta, particles, moving at the speed of light that are just like light, except they don't have a frequency. They don't come at a regular period. Alright. Till next time. Alright, I'll just throw in this bit. It's a little bit soon.
Toward the sun. As a matter of fact, Newton was able to demonstrate that the statement that equal areas are swept in equal times was a direct consequence of the simple idea that all of the changes in velocity are directed exactly to the sun, even in the elliptical case.
Right, even in the elliptical case. Well, really, this is all just, this is the reason for that. This idea that if there was chaos here, there was things moving in all kinds of directions, the ones that won't hit you are always going to be irrelevant. So the ones that will hit you is exactly like a reverse light bulb. There's just no difference. It's exactly like you were the source of the force. The force will come at you the same way, substantially. The substance of the force. I guess there is possible that stuff will come at me in some kind of angle, hit the top of my head, and go through it that way. But I'm just saying it'll all be coming from some location to some the quanta it will hit. Each individual quanta, it has its center of gravity. We have a center of gravity that's subtly different because that's a collection of the net gravity. But each quanta has its own center of gravity, and each quanta will be affected by a world of gravity that equally comes in from all directions. And everything else that doesn't hit it is irrelevant to its existence. The only thing relevant to its existence are the things coming at it the speed of light. And that in relationship to all this other stuff moving the speed of light means that no matter what velocity it's part of, its velocity is always the same, and it can never have anything called momentum. It can't have anything that will that changes its relationship to the universe. It's always going to have the same relationship to the universe no matter what direction it's going in. It's just a different direction. It's not anything else. So even if it's going in a circle, its perspective to the universe is exactly the same. You have to understand the dissection, that once you cross that line from quanta to everything else, that the quanta exist in a world where the only thing that changes is direction. There is no energy transfer. And it's only when you have groups of quanta that you can have this idea of collecting and releasing, which is our understanding of energy. Okay, probably enough. Alright, I think I'll just throw in this bit because, yeah, it's provocative.
To the Earth, and that what we're looking at when we see the moons are not how they are now, but how they were the time ago that it took the light to get here. Now, when Jupiter's near us, it takes less time for the light to come, and when Jupiter's further, it takes longer time, so he had to correct the observations for the differences in time, and by the fact that they were this much too early or that much too late, was it?
Right, so light takes a while to get here, but so does gravity. So gravity has the same problem, and so when things get further away, there starts to become a problem in the sense that the gravity is now not instantaneous. It takes a time to get to a location in terms of the imbalance, and the imbalance will not be reflective, the same. It'll be a different kind of gravity. It won't be a peak gravity because the thing will have moved before the gravity got here, kind of a thing. And this is the Einstein part of the progression in Mercury's orbit that Einstein compensated for was kind of, sort of, a phenomenon like that, in the sense that things close to the gravity will be affected by any changes in the gravity. Things further away are less likely to be affected, first because the gravity is much weaker, so the percentage of any fluctuation in gravity won't be felt. And so the sun, being a very volatile thing, changes its magnosphere, its plasma, and its center of gravity. And that change, that Brownian motion, another Einstein concept, this shudder the sun has, will be felt by Mercury more than any of the other planets because of its closeness to the sun. Let's play some more of this.
Able to determine the velocity of light. This was the first demonstration that light was not an instantaneously propagating material. I bring this particular matter to your attention because it illustrates something. That when a law is right, it can be used to find another one.
Right, so that's sort of my principle here. When a theory is right, when a concept is right, it'll show you things in other things. So again, we have this idea of this inverse square relationship. It exists in magnetism and electricity. It should give us an indication that these things are connected. Now the other thing it gives you is an understanding that atoms and the pieces that make them up have a kind of metabolism. They have a structure. And if that structure is obliged to move, that means the parts inside of it have to move. And if the parts inside of it are made out of something already moving, they can't move faster than the speed of light. So if a piece of us is going this way at the speed of light, and we move, obviously it can't go faster, so it can't accommodate that movement. Something else has to accommodate the movement, some other process over time. Some extra arrows have to be collected to make it possible for us to do that moving. And the metabolism of that movement has to change. So if it's doing this, and I oblige it to do this, it's going to do this slower. So if it's doing this, and I say you also have to go that way, it can't do this at the same speed, because now more of the arrows have to be going that way. They can't go this way, that way, that way. They have to be going that way, and to do that, they're going to have to consume this other motion. They're going to have to use the time it would have been using to go these other directions. It's going to spend some of that time going that way, because some arrow has to be changed. Some arrow going this way or that way or that way. So that metabolism slows down. So this concept explains time dilation. So like Feynman is saying here, that's a good indicator of a theory being right.
By having confidence in this law, if something is the matter, it suggests perhaps some other phenomenon. And if we had not known the law of gravitation, we would have taken much longer to find the speed of light, because we would not have known what to expect of Jupiter's satellites. This process has developed into an avalanche of discoveries. Each new discovery permits the tools for much more discovery. And
so I would argue that they stifled that entire process, and Feynman was part of that, in my opinion. I mean, a nice guy, but he's part of that. By, in the 1900s, established the early 1900s, playing this idea of a wave concept of photons, giving them all kinds of properties, giving them all kinds of power, nuance. So taking the smallest bits and giving them the authority. Then Einstein comes along and does something even though he didn't like action, spooky action at a distance. He didn't like wave. He liked particle. He took it even further and then gave space power and made space the thing that's making things happen. That somehow the space forces things to fall, which intuitively bell should have gone off. Something should have happened. So in this 400 years of blah blah blah, this was a critical mistake in physics, and now physics just keeps trying to make these pieces fit, and they won't fit because they're wrong pieces. All force is made of one force. It's all one thing, directional information, and you're just have an illusion. Matter's just trapped energy. E equals mc squared should be taken literally. Matter is energy. It's not what energy is, it's what matter is. Energy isn't matter. Matter is energy. Trapped.
This is the beginning of that avalanche, which has gone on now for 400 years in a continuous process.
Yeah, and I'd say it was continuous, and then, like I said, until the 1900s, when it all went south with bizarre interpretations of a few abstract experiments that were on the surface confusing because they duplicated something. It sounded like a dog barking, but because it sounds like a dog doesn't mean it's a dog. A panda bear looks like a bear, but it's a raccoon. That kind of thing. sometimes things fool you. There's a lizard that doesn't have any legs. It's not a snake. It's still a lizard. But it looks like a snake.
And we're still avalanching along at high speed.
Yeah, well, you're less than the speed you should be at, in my opinion. But anyway, I'll be back. Alright, just play this a little bit.
More recently, in the beginning of the 20th century, it became apparent that the motion of the planet Mercury was not exactly right. And this caused a lot of trouble and had no explanation until a modification of Newton's. This did show ultimately that Newton's laws were slightly off and that they had to be modified. I will not discuss the modification in detail. It was made by Einstein.
Yeah, I think he didn't want to do the detail because, yeah, it doesn't really work. I'm just saying it as a detail. I mean, it's way too detailed is the problem. And it really wasn't a flaw in Newton. It's just that, yeah, Newton didn't know the sun was shuddering or, this, you know, all these other properties of these active bodies he couldn't account for. But there's nothing fundamentally wrong. It's just this is an added effect. It's just something else in the system. It's an addition to Newton. It's not a subtraction from Newton. It's not a change of Newton. It's just that Newton didn't account for. He didn't include it. It's just something excluded from Newton, not something wrong with Newton. Yeah, be a better way to say it, I think.
Now the question is, how far does this law extend? Does it extend outside the solar system?
Okay, well this part you don't need. Just this idea of big. You know, the whole universe is run by this force. And that's my whole point. We see it in this little scale of just the sun and the earth and the moon and the earth. And yeah, it goes into these galaxies and it goes into these nebula and it goes into these clusters and it goes into this whole giant, huge universe that is huge. And we don't have a problem seeing gravity grow out that way, and somehow we have a problem seeing it go down into the micro. So that's the kind of irony here, is that there's a huge expanse of size difference, space between things difference, and what we see as matter is quanta compressed. Kind of. But there's a huge, the expansiveness, the density of the universe, the size of it is just huge. But it's all one thing at the core. It's all the same stuff happening. It's just different locations of condensation, just droplets pulled out of the vapor, so to speak. Rain. Matter is just kind of rain coming out of the cloud of quanta. Something like that. Should stay away from any metaphors if I can. Anyway, till next time. I just threw this in. So he's talking about how gravity of the forces is atypical in the sense that it doesn't have a whole lot of application. I mean, certainly we can't extract anything from it. We can figure out that, yeah, it's keeping us stuck on the Earth. It has some application to understanding where satellites will end up and all this kind of thing, but it doesn't have anything that we can eat, so to speak. You know, you can't glean energy out of it on this level of it. But that's the trick, is they have to understand that all the other forces are gravity. So we can manipulate gravity when we can manipulate the bodies. If we were big enough to play with the Earth and the Moon, we could extract energy from them. But we're not big enough to take advantage of the force because we can't move the Earth and the Moon. That kind of thing. So I'll play a little bit.
Typically, among all the other laws of physics, gravitation has relatively few practical applications. I mean, the new knowledge of the law, it has a lot of applications. It keeps people in their seats and so on. But the knowledge of the law has few practical applications, relatively speaking, compared to the other laws. This is one case in which I picked an atypical example. It is impossible, by the way, by picking one example of anything, to avoid picking one which is atypical in some sense.
Yeah, well, whatever. I don't know about that one either. I don't think it's impossible. Right, I think it's like the idea that something could fall into a perfectly circular orbit. It's just not likely. And it's not likely that you'll pick the atypical, the typical. Well, yeah, it's pretty likely, depending, you know, if you're picking out of some jar that has the same shit in it. Well, anyway, that point doesn't matter. We'll move on. Well, I'll throw this one in just because it's a little opportunity for me to take a counter punch.
Modernly, in working out the motions of the satellites and planet probes and so on that we send up, and also modernly to calculate the predictions of the planet's position, which have great utility for astrologers to publish their predictions and horoscopes in the magazines. That's the strange world we live in, that all the advances in understanding are used only to continue the nonsense which has existed for 2,000 years.
Okay, so it's good to take a shot at the nonsense, right, of astrology. But I would say that your version of quantum mechanics was nonsense. Multiverses, Copenhagen interpretations, all of this mumbo-jumbo was effectively, you know, bizarre extrapolation, and nobody did anything to put that in any kind of container, and it ended up creating experiments that never took place about photons that can read our mind and all kinds of pop culture nonsense that has become part of theoretical physics. And it's just pop culture nonsense. It's no better than astrology. It has no scientific evidence, and it doesn't even have intuitive reasonableness. It's got nothing going for it except it's what people want to hear, just like astrology. So, bad on you for being part of that. Yeah. Alright, here's a little bit worth something, maybe.
It means, for example, that in a satellite, a man-made satellite, an object inside will go around the Earth in the same kind of an orbit as a satellite on the outside, and thus float in the middle, apparently. So that this fact that the force is exactly proportional to the mass and that the reactions are inversely proportional to mass has this very interesting consequence.
Yeah. Now the consequence really is that it's actually the tiniest bits that are creating that circumstance. It's the gravity is affecting the smallest bits of the atom. And even if you thought about it affecting just the atoms, it's just the atoms that are really being influenced by gravity. Your matter, your body is not being affected by gravity. It doesn't like hit your surface of you and push you. It's affecting every single nuclear piece of you. Every bit of you is being affected. It's in a universe and it's feeling a gravity on all sides. And then when there's this imbalance of the force, the arrows, there's more arrows going down because the Earth is blocking them from coming up. Every bit of me is being hit by those arrows and is exchanging directional information, which is obliging my body to go down. I can't go down because the ground's stopping me. But I am actually going down. The matter inside of me is going down. The arrows are being converted. My body's exchanging arrows. It's creating more arrows going down. But who's that? Armando. Oh, I'm gonna right there. Yeah, okay. I'll answer that. Try it here. I'll be back. Oh, it was an unpleasant waste of time. But anyway, back to it. I'm running out of time, unfortunately.
I should say something about the relation of gravitation to other forces, to other parts of nature, other phenomena in nature, and I'll have more to say of a general quality later. But there is one thing that's particularly interesting, and that is that the inverse square law appears again. It appears in the electrical laws, for instance, that electricity also exerts forces inversely as a square of the distance, this time between charges. And
yeah, like I said, it also applies to magnetism. And it should be understood that the inverse square is this straight line kind of force, and so that should be an indicator. The idea of straight line force radiation.
one thinks perhaps inverse square of the distance has some deep significance. Maybe gravity and electricity are different aspects of the same thing. No one has ever succeeded in making gravity and electricity different aspects of the same thing. Today...
Yeah, well, and they partly didn't succeed because people like you would debunk them with, I think, a less than respectful, complete effort to appreciate possibility.
Our theories of physics, the laws of physics, are a multitude of different parts and pieces that don't fit together very well. We don't understand the one exactly in terms of the other. We don't have one structure from which all is deduced. We have several pieces that don't quite fit exactly yet. And that's the reason why in these lectures, instead of having the ability to tell you what the law of physics is, I ask talk about the things that are common to the various laws, because we don't know, we don't understand
yeah, and partly because you would say things like, just keep doing the math and don't bother thinking about the mechanism. And I think physicists should have tried harder.
Connection between them, but what's very strange is that there are certain things that are the same in both. But now let's look again at the law of electricity. The law goes inversely as the square of the distance. But the thing that is remarkable is the tremendous difference in the strength of the electrical and gravitational laws.
All right, now, let's see, I'll hopefully play more of this, but, you know, it's really irritating that I'm running out of time. Just because the difference in the strength of them is ironic, is because it's just so obvious. And it's obvious if you understand this quanta. I mean, he's famous for quantum electrodynamics, you know, doing lectures on that subject. And it's just so ironic because if you understand it as a quanta field that's doing the interacting, that is the foundation of the mechanism, then you understand that when you make it bigger and bigger and bigger, when you apply the energy at a closer and closer level, smaller and smaller, it's more and more direct. Quanta interact 100% or 0%. So it's all or nothing in terms of their interaction. But on the bigger level, there's lots and lots and lots of empty space. There's no one-to-one correlation anymore. There's not one arrow hitting another arrow. There's one arrow hitting another arrow in a dense field of empty space. So the difference in the strength of the force is merely a reflection of the fact that there's so much more empty space in the bigger object. So when you get to the size of an Earth, the amount of empty space, not arrow, is huge. And when you get all the way to the quanta, the amount of empty space is 0. And so that's the linear connection. That's the reason why there's such a dramatic difference, is because of the amount of probabilistic non-event. The amount of non-event versus the amount of event at the quanta level. I think that's one way to say it, but it's just about the empty space. As you get further and further and further away from the atom, the nuclear parts, the quanta, you get more and more and more expansive empty space.
People who want to make electricity and gravitation out of the same thing will find that electricity is so much more powerful than gravity that it's hard to believe they could both have the same origin. Now, how can I say one thing is more powerful than
So
another?
one is almost just above the nuclear. Electricity is really close to a nuclear force, and the other is planetary. I mean, it's huge, you know, huge objects. So again, it's that difference in the size of the object that is the difference in the force strength.
Depends upon how much charge you have and how much mass you have. I'm certainly...
So you can't go by mass, because the mass of the quanta is all complete. It's got a, you know, it's completely equal to the force applied to it. It's